So as I told you yesterday, today's lesson is actually going to be on the next unit. It will not be on our um, test that's upcoming. And our test that's upcoming is probably Thursday next week. Maybe it's Tuesday next week. It's one of the two. Yeah, Tuesday of next week. So this part won't be on that exam. So we're going to look at Taylor polynomials and approximations. So before we leap into all the words here and there's a lot here. But remember that one of the things that we did pretty early on is we said, all right, if we have a function like this and we were to draw the tangent line, that as long as we were really close to this point, the tangent line's a pretty good approximator. Okay? So at some point, somebody, I think pretty smartly, went, well, what if instead of just having a linear function, what if we had a quadratic function? How could we build a quadratic function that went through this point and kind of hugged this a little bit better? So it's a little better for a little longer. And then once they did that, the dam was burst, and they're like, well, what if we made a 17th degree polynomial for that? And how could you do it? So that's what we're going to look at today. How can you make a polynomial function that approximates another function? This was especially helpful before some of the things in better computing power, where computers basically could add, subtract, multiply, and divide. They could do those things really fast, but they couldn't do a whole lot more. Well, if you have a polynomial function, everything in a polynomial function is add, subtract, multiply, and divide, right? So you could get really good approximations this way. All right, so for any function f of x, we can write a polynomial approximation p sub n of x with degree n. So this would be like the 5th degree polynomial, or the 17th degree polynomial would be n. Now, how do you make it to where it's good? Because you could write one, but it's like, well, yeah, it kind of goes through that. So if I go back up to this, if I have my quadratic looks like this, we're like, well, that's a really crappy approximation, right? It's okay right here, but as soon as you get any distance away from the point, it's no longer any good. So what do you do to make it to where it's good? This is the genius part. If we further require that the first n, whatever that number is, derivatives of f at some centering point C, so this is where we're centering our approximation, be equal to the first n derivatives of p sub n of x, we can have a really good approximator. So how does that work? All right. And I know this looks like a ton, but we're going to go through it pretty slowly. So what you do to start with is you write the general nth degree polynomial. It's going to have a constant, a sub 0, plus a constant times x minus c. Up until then, what does this kind of remind you of?
It's a linear.
I'm sorry?
It's like a linear function.
Right. This is point slope form. Right? This is part of why I have always thought point slope form is way more important, because it starts off with the tangent line approximation. And then you're going to add on a quadratic term and a cubic term, and you're going to keep going through whatever term number you want. So what we're going to do, first of all, we want our approximator to go to intersect the function at x equals c, right? So what we're going to require is that f of c be equal to P sub n at C. And notice at C, what's going to happen to all these terms? If x is equal to C, what's going to happen to all these?
Zero.
They're all 0. So the only thing you're left with is a sub 0. So we're going to make the value of the function be equal to a sub 0, which is, right, point slope. All right, where did it start? And then we're going to take the derivative of this enormous polynomial, and notice the first term drops off, and then the derivative of the second term, since that's linear, is just going to be a sub 1. And then we'll have 2a sub 2 times x minus 2, x minus c to the first, and we'll have 3 times a sub 3, x minus 2 to the third, etc., etc., etc. Everybody goes down a power. But the coefficient is multiplied by the old power. Well, now if we take the derivative, f prime at c, we want it to be equal to the nth derivative, or excuse me, the derivative of p sub n at c, and that's going to be equal to a1. And at first you may just think, oh, I just need to, each one of these is going to be the derivative, that this will be the function at c, this will be the derivative of the function at c, this will be the second derivative of the function at c, the third derivative of the function at c. Unfortunately, this would be a case of, if you thought that, then you haven't looked at what the next one is. When we take the second derivative, now we've got 2 times a sub 2. Right, we no longer have just a sub 2. Plus 3 times 2 times a sub 3, etc., 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 on down the line. So our second derivative at c needs to be the second derivative of f at c is going to be 2 times a sub 2. So a sub 2 is going to be equal to the second derivative at c divided by 2. That's going to be my quadratic part's coefficient. And if we do it again, then when we have the third derivative, now we've got 3 times 2. You're like, oh, okay. So this is getting worse. But if you recognize that as, oh, 3 times 2 is same as 3 times 2 times 1, this is 3 factorial. So what happens is our third derivative ends up being 6 times a sub 3, so a sub 3 is the third derivative over 3 factorial. From there, the pattern continues to where the when we take the nth derivative and we only have, this is the only thing we have left, we're going to have multiplied by n, and then by n minus 1, and then by n minus 2, and then n minus 3 each time we take the derivatives, to where we have n factorial times a sub n. So a sub n is going to be the nth derivative at c divided by n factorial. In fact, if we went back to, you're like, well, could I have made this 2 factorial? Is 2 equal to 2 factorial? Yeah, we could have. Could we have said that a sub 1 is equal to f prime at c over 1 factorial? Yeah, and in fact, we could have gone all the way back to here to say a sub 0 is going to be f of c over 0 factorial, because remember, by definition, 0 factorial is 1. So it actually works for all of them. Sometimes students are like, I don't like that it's a different rule for each one. Well, it's actually the same rule for all of them. So this leads us to something that's called Taylor and Maclaurin polynomials. There's a long, ugly history with this. It turns out that the one that we call Taylor polynomial was actually worked on more by Maclaurin, and the one that we call a Maclaurin polynomial was worked on more by Taylor. I don't know how it happened, but it's one of those things in math history where somebody screwed up and it didn't get caught quickly, and so we're stuck with it. So if a function f has n derivatives at c, where n is just some positive integer, then p sub n of x, which is the polynomial of degree n, is going to be equal to this ugly hairy hose beast thing that we had before. But now, instead of just having constants that are in terms of a, where we didn't know what anything was, now our constants are the value of the function at c. And if you want to put over 0 factorial, that's fine. And then the first derivative at c over, if you want to put 1 factorial, that's fine. The second derivative at c over 2 factorial times x minus c squared. The third derivative at c over 3 factorial times x minus c to the third, all the way to the nth derivative of f at c over n factorial times x minus c to the n. This is called the nth Taylor polynomial for f at c. If c happens to be equal to 0, in other words, if we center our approximator at 0, then we have p sub n of x is equal to f of 0, f prime of 0 times x, f double prime of 0 over 2 factorial. And you notice that how many derivatives you take matches this, which makes it pretty easy. That's always going to be true. That's called the Maclaurin polynomial of f. You can also call it a Taylor polynomial for f centered at 0. It's the same thing. All right, so let's do this. Let's find the 7th Maclaurin polynomial for e to the x. So we need to have f of x is e to the x, and f at 0 then is e to the 0, which is 1. And f prime of x is, well, e to the x. And f prime of 0 is also 1. And this just continues. F double prime of x is e to the x. F double prime at 0 is 1. And I'm not going to write all of these through the 7th derivative. Remember, that's read f super 7. We haven't done that very often. At 0 is also going to be equal to 1. So my 7th degree polynomial, p sub 7 of x, is going to be equal to, we start with just the value of the function, 1, plus the derivative, 1, times x minus c. And I know that it's 0 and I don't have to write it. I think it's just a good habit to get it into, of just always writing x minus wherever I'm centered. Okay, so far what I've got is the tangent line approximation. I mean, these start with the tangent line approximation, but then they go on. So this will be 1 over 2 factorial times x minus 0 quantity squared, plus 1 over 3 factorial times x minus 0 quantity cubed, etc., etc., etc. through 1 over 7 factorial times x minus 0 to the 7th. So p sub 7 of x is equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial plus x to the 5th over 5 factorial plus x to the 6th over 6 factorial plus x to the 7th over 7 factorial. I think on another day we will actually look at what does this polynomial look like? You know, and how good is it? I don't think we do that today. If we did, I'm not really prepared. Let's go on to the next example. So here, find the Taylor polynomial P sub 4 for f of x is natural log of x, centered at x is equal to 1, and then use P of 4 to estimate the natural log of 1.1. This is a lot like, remember when they would ask you to write the equation of a tangent line and then use it to approximate the function? It's the same thing, it's just we're using a polynomial instead. So the approximation is typically a lot better. So f of x is the natural log of x. F at 1 is the natural log of 1, which is 0. Turns out that the constant term on this one drops out. F prime of x is, it's 1 over x, but I'll write it as x to the negative 1 because I know I need to take the derivative of it multiple more times. So f prime at 1 is 1. F double prime of x is going to be negative x to the negative 2. So f double prime at 1 is negative 1. F triple prime of x is 2x to the negative 3. So f triple prime at 1 is 2. And then f super 4 of x is going to be negative 6x to the negative 4. So f super 4 at 1 is negative 6. So my Taylor polynomial, P sub 4 of x, is going to be equal to, and again, I kind of overdo it. I write out everything and then I simplify it. So I'm not going to just ignore that. I'm going to go, okay, 0, because I might forget something later. And then I've got 1 times x minus 1. And then I've got negative 1 over 2 factorial times x minus 1 squared plus 2 over 3 factorial times x minus 1 cubed minus 6 over 4 factorial times x minus 1 to the 4th. So then P sub 4 of x is going to be equal to x minus 1 minus x minus 1 squared over 2 plus 2 over 3 factorial is 1/3. So it's x minus 1 to the 3rd over 3 minus 6 over 4 factorial is 1/4. So we have this nice polynomial function that we can use to approximate natural log. And because this one is an alternating series, if we wrote, it's not an infinite series, right? It's a finite series, which we don't normally talk about. But if I wanted to estimate natural log of 1.1, now I can just substitute in 1.1. So that's going to be 1.1 minus 1 minus 1.1 minus 1 squared over 2 plus 1.1 minus 1 cubed over 3 plus 1.1 minus 1 to the 4th over 4. And I should not have put an equal sign here. I should have put, that's approximately equal to. If this is the AP exam, it's all numeric. You're welcome to leave it. I'm going to go ahead and see if I can simplify this a little bit. So this is going to be 0.1 minus 0.01 over 2 plus 0.001 over 3 plus 0.0001 over 4. And I'm curious what that comes out to be. So it's 0.1 minus 0.01 divided by 2 plus 0.001 divided by 3. Did I miss a sign? Oh, I messed up a sign right here. It's like this was supposed to be alternating. Minus 0.0001 over 4. And that's 0.0953. If you were actually to do the natural log of 1.1, it's 0.0953101798. And if you took this out to more decimal places, it's 0, and then this is where it diverges from the other 8333. But you can see it's pretty accurate. Partly it's pretty accurate because I'm not very far away from my centering point. Remember, we had that happen when we were doing tangent lines, right? When you're close to the point of tangency, the tangent line's a really good approximator, but you get very far away and it gets bad. What we're eventually going to find is that if we change these from a polynomial to an infinite series, then in some cases it stays with the function all the time. It's actually not just an approximator, it is equal to the actual function. All right, let's find the Maclaurin polynomial P sub 6 for f of x is equal to cosine of x, and then use it to estimate cosine of 0.2. All right, so f of x is cosine of x. It's a Maclaurin polynomial, so we want what is f at 0. Cosine at 0 is 1. The first derivative is going to be negative sine of x. The first derivative at 0 is going to be 0. So on this one, the second term is going to drop out. We take the second derivative of x, and we're going to get negative cosine of x. So f double prime at 0 is going to be negative 1. Then the third derivative at x is going to be positive sine of x. So the third derivative at 0 is going to be 0. Then f super 4 of x is going to be back to cosine of x. So f super 4 at 0 is 1, and then this is going to repeat itself, right? So without having to work everything out, f super 5 at 0 is going to be 0, and f super 6 at 0 is going to be negative 1 keep following that same pattern. So my 6th degree Taylor polynomial, or Maclaurin polynomial, p sub 6 of x, is going to be equal to 1 plus 0 times x minus 0 minus 1 over 2 factorial times x minus 0 squared plus 1 over 3 factorial, excuse me, 0 over 3 factorial times x minus 0 cubed plus 1 over 4 factorial times x minus 0 to the 4th plus 0 over 5 factorial times x minus 0 to the 5th minus 1 over 6 factorial times x minus 0 to the 6th. So simplifying that, we get 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. So my estimate, p sub 6 of 0.2, is just 1 minus 0.2 squared over 2 factorial plus 0.2 to the 4th over 4 factorial minus 0.2 to the 6th over 6 factorial. And in the interest of time, I'm not going to calculate that or show how close it is. Now, all this said, on the AP exam, if you are asked to make a Taylor or a Maclaurin polynomial, they are almost never going to give you the function. Instead, they're likely to give you values of the function and values of its derivative, right? So you're not having to do this part up here, okay? There's two reasons for that. One is that unless it's a really simple function, taking the derivative can get pretty awful. The second part is, if it's something where taking the derivative is pretty easy, students have probably actually memorized that one because it's come up often enough. Okay? All right. And again, bad teacher. It should be an approximation. It's not equal to that. It's close to that, but not actually equal to that. Oh, one thing just I'll point out real quickly. What do you notice about all the powers in this polynomial? They're all even. And if you remember from pre-cal, hopefully you talked about this, that cosine is an even function, right? Because it's symmetric with respect to the y-axis. It turns out, had we done this for sine, all of my powers would have been odd. And sine is an odd function. I've always found that fascinating. I was like, that's pretty cool that, you know, this thing that we talked about without any relationship to this continues to have the same relationship, right? It's all odd powers. And it makes sense. If I want to approximate an odd function, that I should have a polynomial with all odd powers. All right? Is this the last one? Yeah. All right, find the third Taylor polynomial, and that should say third degree. Now, please add that in. Taylor polynomial for f of x is equal to sine of x expanded about x equals pi over 6. This gets a little hairier because you don't have a whole bunch of terms that drop out. So f of x is sine of x. F at pi over 6, let's see, sine at pi over 6 is what? It's 1/2. F prime of x will be cosine of x. So f prime at pi over 6 is square root of 3 over 2. Then the second derivative of f at x is going to be negative sine of x. So the second derivative at pi over 6 is going to be negative 1/2. And we wanted the thirds, we've got to go one more. F triple prime at x will be negative cosine of x. So f triple prime at pi over 6 is going to be negative square root of 3 over 2. So our p sub 3 of x is going to be 1/2 plus the square root of 3 over 2 times x minus pi over 6. And this is part of why I'm like, even when I'm doing Maclaurin, I write the minus 0 at first to remind myself, oh yeah. The problem is you can do so many Maclaurin that when you do a Taylor, you suddenly forget, yeah, I've got to do x minus wherever I'm centered. And again, this is just the tangent line approximation. Then minus 1/2 over 2 factorial times x minus pi over 6 squared minus square root of 3 over 2 over 3 factorial times x minus pi over 6 cubed. So that's going to be 1/2 plus square root of 3 over 2 times x minus pi over 6 minus 1/4 times x minus pi over 6 quantity squared minus the square root of 3 over, what, 12 times x minus pi over 6 quantity cubed. So you can center these wherever you would like. In terms of being a realist, you know, when you center this at pi over 6, it just gets a lot uglier. A lot of times we center around something convenient. So for example, for sine and cosine, centering it to 0 is very convenient. You'll notice that for natural log, you're like, we didn't center that at 0. Well, that's because none of these things exist at 0. Natural log doesn't exist at 0. So how can you center your approximation around that? So we use 1. You could make a case for using E also. And that would work pretty nicely. But generally we pick something easy to center things around. Now, again, as I said, on the AP exam, they're likely to give you these values. They'll probably give you some other values as a smokescreen, you know, things that you don't need, and you just go straight to this. Okay? Any questions? All right.